last lecture, we have been discussing the continuum mechanics applied to the case of a polymer network, that is rubber, and we have obtained the expressions for the stress, the shear modulus, and so on. We discussed the shear deformation of rubber. So today I will take the discussion further, talk about uni axial deformation for the polymer network, and after that I will take you to what is known as a microscopic definition of stress tensor that I will continue in the following lectures. So just to recall, we have discussed that the polymer network where these circles are my cross links, and between two cross links I have strands. I can write the free energy of this network as a function of the deformation tensor, and using that idea we have obtained the shear modulus as G is equal to NC kBt, where NC is the number of strands per unit volume. And we have been discussing the case for a shear deformation. So for a shear deformation, the stress applied is something like G multiplied by gamma, where gamma is the shear that is applied and or shear that is obtained after application of a stress of sigma, and sigma is the stress, and this is my shear modulus. So before we go into uniaxial deformations, there is one point I want to make here, that if I want to know the magnitude of this shear modulus, how does it compare to other materials, it is useful to look at the bulk modulus of an ideal gas, for example. So the bulk modulus of an ideal gas is given as something like K is equal to N kBt, where N is the number of molecules per unit volume, which shows some similarity with the expression we have NC kBt. Here also we have something like numbers per unit volume or number density, but now we have number of strands per unit volume. But the key idea here is, just like the bulk modulus of an ideal gas is very small, ideal gas is not really highly stiff in that sense, it is very soft, I would say as soft it can be. So in same sense, the shear modulus of a polymer network is also very small, and that explains why the polymer network is very soft. That is, it will respond to deformation or applied stress much easily than compared to materials like metals, which will have much higher shear modulus. So if the shear modulus is small, that means we are having a material that is very soft in nature. So this kind of explains that the polymer networks are soft materials. As opposed to, say, hard materials like metals and so on, it is really soft. We already have said that it is not quite solid when I compare that to a metal. If I add a little bit amount of liquid, it becomes a gel that is more liquid like. So, polymer network in solid form is somewhat like a solid, but it has a very small shear modulus. That explains why it is very soft. If I apply even little amount of stress, it will deform. In fact, if I want to increase the modulus, one way is that I can increase the number of cross links. The more cross links I am going to have, the more stiff the network will become. And so, the cross link density in some sense is a measure of the elasticity. As I increase my NC, I would decrease the elasticity of the material, or in other words, it is less soft as we increase NC. And this is the way we can obtain materials of different stiffness by varying simply the cross link density. And the kind of experiment I propose to you is, we have a polymer solution and we add a cross linker. So, as I increase the amount of cross linker for given concentration of polymer solution, I will form different kinds of materials, different kinds of network, which will vary in the rigidity or stiffness. More cross linkers will give you more stiff materials, less cross linkers will give you less stiff material. Of course, in the limit when there is no cross linker, we have a liquid, and in the limit when there is plenty of cross linker, we have a very hard solid that we can think of. And of course, we are always between these two extremes, and we have materials of shear modulus still very small, although the material keeps its solid nature as long as the cross linking is covalent in nature. If it is like a physical cross linking, like say entanglements, then in that case, if I apply some deformation, these cross links can really break. That is not assumed in the case of a covalent cross linking. The cross links will be stable, but the materials will respond to deformations very easily, and that's why these materials find a lot of use. Okay, so let us now talk about another type of deformation that is called uni axial deformation. And the idea here is the following. We again start with a material. Again, I am not doing in the perpendicular direction. So, let us say this is my Z, this is my X, and this is my Y. So, I am just drawing in X and Z, but you can assume that there is also a Y direction, just like we have the X direction. So, in 3 dimensions, it is going to be something like this. Okay. So, when I deform this material along the Z direction, by applying some stress, let us say sigma from both the ends, and assuming that we started with unit dimensions, that is 1 1 1 on all the sides, the final state will have some value, some length lambda along the Z direction, and since the material has to conserve volume overall, as we stretch in one direction, it has to thin in the other 2 directions. So, if I start from here, I am eventually going to a shape like this, where we know that the z direction is lambda, and the other two must be much smaller. And since we cannot differentiate between the x and y direction in this case, because deformation is being applied in z direction, these two must be same. Let us call that A for a moment. This is my final state. This is my just a 3D drawing of what I have drawn here, and then this is my initial state, and of course the volume has to be conserved. So, this means that the initial volume, which is simply 1, is equal to lambda multiplied by A square, that is the final volume. This gives me the value of A is equal to 1 by square root of lambda. So, let me write down here. Okay. So, it is the deformation in x and y is because of the stress being applied in the z direction, and the reason why it is happening is because the material is somewhat incompressible. Okay. So, now I can write the deformation gradient tensor in this case again as what we have been doing for the simple shear deformation. It will have 9 components like this, and these components will be given by dou x prime by dou x, dou x prime by dou y, dou x prime by dou z, dou y prime by dou x, dou y prime by dou y, dou z prime, dou y prime by dou z, dou z prime by dou x, dou z prime by dou y, dou z prime by dou z. Okay. Where again we have assumed that we are going from initial state x, y, z for every material point in the volume, and we are assuming that the deformation is uniform. That is the same assumption we have used earlier as well, that is every point is undergoing same deformation or similar kind of deformation. So, then I can write here x prime as 1 over square root of lambda x, y prime is 1 over square root of lambda y, z prime is equal to simply lambda multiplied by z. So, this gives me only the diagonal components in the matrix, and you can see that all the off diagonal components are going to be 0. All right. So, now if I look at the free energy density for deformation, we had derived the equation for polymer network as this, where NCKBT is my shear modulus as we just defined. So, we can also write it as half of G and this term we can write as Exx square plus Exy square both alpha and beta are dummy variables here, E xz square plus E y x square plus E y square plus E yz square plus E zx square plus E zy square plus E zz square minus 3, and as we had just noticed, all the off diagonal terms are going to be 0 and we are only left with the diagonal terms, which you can see for x and y it is 1 over square root of lambda, and for z it is lambda. So, the first term is 1 by lambda, the second term is 1 by lambda, and the third term is lambda squared, and so we are going to have half of g lambda square plus 2 by lambda minus 3 for this case. Okay. So, now if I want to find the force that is acting on the surface, that is perpendicular to the xy plane, that is the surface I will highlight here. If I look at the force that is acting on the surface, it will be the stress multiplied by the area So, we have sigma, that is now a function of lambda, that is the force per unit area. If I multiply by the area, that is 1 over lambda, that gives me the force. That force, if I multiply with d lambda, that tells me the free energy change for a small deformation from lambda. So, assuming that the lambda is my mechanical equilibrium state, and if I do a small deformation, then the change in free energy is the force acting at that moment when the deformation is lambda, that is what we have here. This is the force at deformation lambda multiplied by the d lambda, the small lambda of deformation, that is when we go from lambda to lambda plus d lambda, and this will be equal to the change in the free energy. So, this means that the stress can be written something like this, and since we have already obtained the expression for F, we can get this as that is simply okay. So, now there is a bit of a problem in this equation, since we assume that the free energy varies like the energy of an ideal chain, there is no term in this equation that will prevent the stretching of chain to unphysically high values. Okay. But in reality, if I stretch the polymer network, there will be a moment where all the strands are stretched to the maximum possible contour length, and beyond which there can be no extension. So, in reality, there is a limit on the maximum stretching that can be given by the ratio of the maximum possible contour length of a chain or a strand in this case multiplied by the average length for an ideal chain, and this is given by square root of n. So, this pose a limit that we can refer as the finite extension limit, which is not captured by the model that we have discussed. Of course, we can make corrections to it. So, whatever we have developed is only applicable for a small deformation. It is the same idea that goes to the previous point, that in any case the change in free energy on deformation is equal to the work done, is something that applies only when we are very close to equilibrium, not very far from it. Very far from equilibrium, the whole idea of free energy becomes somewhat crude, or I would say not quite accurate. Thermodynamics only works near the equilibrium. So, with this kind of a framework, if I now want to find the Young's modulus, in the earlier case when we are doing the shear strain, when we are applying a shear, we looked at the shear modulus. Now we are like stretching the material like this. So, we are applying a strain normal to the plane as opposed to tangential to a plane. So, now we can define what is known as the Young's modulus. So, if I write for example lambda as 1 plus epsilon, epsilon being my strain, then from what we have derived, stress is lambda square minus 1 by lambda multiplied by g. This will be 1 plus epsilon squared minus 1 by 1 plus epsilon. So, the first term I can expand always, the second term I can expand for small values of epsilon, where we have the series 1 minus epsilon plus epsilon square and so on. So, for small epsilon or small strains, I can write this as again we have certain cancellations here. And what we do get is now, since Young's modulus is defined as the ratio of the stress to the strain, the Young's modulus is equal to 3 times G for the case of a polymer network. Okay. So, this is like the procedure that we can adopt once we know the expression for the free energy. We can go ahead and try to find constitutive law based on the ideas we have discussed, and using that we can look at the governing equation of motion, and then we have the complete picture of the dynamics of the polymeric system or any system for that matter. So, although we have discussed the case of polymer network, you can apply similar analysis for the case of a gas or a liquid or any material. The only problem you will have is you will have to have different expressions for the free energy. They may depend on the deformation gradient tensor as well as the velocity gradient tensor, or maybe like either of them. In any case, both of them are also related by an equation we have discussed. And then what we have is what is known as the constitutive equation, and this completes the continuum mechanics framework for the study of any system. All we need is a constitutive law that relates the stress with the deformation or the history of deformation of a system. So, although I will not derive it, but you may have done this kind of things in solid mechanics or fluid mechanics or transport phenomena course, depending on your background. I am just reproducing some of the results that applies for different class of materials. For example, if we have an ideal elastic material, the constitutive law is, and this is the general expression that also accounts for compressible substances. If it is incompressible, then we can have simplifications to this expression. And if you have an ideal viscous fluid, or what is known as a Newtonian fluid, the expression we have something like this. So, we have discussed the constitutive laws for different class of materials. We have done a derivation for the case of a polymer network. We looked at the shear modulus, bulk modulus, and so on. I am not going in details about other polymeric systems for the lack of time in this course, but the analysis can be applied with some generalizations using the idea that we have to first write the free energy of the system, and then from there we have to get the constitutive law, and from there we can do a continuum mechanics framework. So, I want to remind you here one thing that we did earlier. Earlier also we were doing dynamics using the idea of Brownian motion. We talked about the Langevin equation, and we talked about the Rouse models and Jim models of polymer chains, looking at the diffusion behavior. All of them were for things at equilibrium, but now the similar models can now take some of the framework that we have now discussed in the continuum mechanics, and using that we can then look at the effect of deformation on these materials in the context of dynamics beyond equilibrium, although close to equilibrium, but beyond equilibrium. And this is how this dynamics would be different from the motion of polymer segments, for example, by Brownian motion. Okay. So, earlier we could get the diffusion coefficients, for example, and in these cases we can get viscosities, for example. Okay. And then there are a whole lot of detailed models for various kinds of polymeric systems. There is a whole literature on the constitutive laws that applies to different polymeric systems like polymer gels, polymer solutions, polymer melts, and so on. But the basic framework starts from the thermodynamic descriptions of those systems, and then trying to couple it with the continuum mechanics framework that we have discussed. And we will do one of these analysis in the next lecture when we look at what is known as the microscopic definition of the stress tensor. So, with that I want to conclude here. Thank you.